That is the expression of dissipation. So this is the constitutive model for these kinds of materials. We see that all materials based on decomposition of the strains into elastic and elastic part are characterized by this constitutive equation and that equation of dissipation. Okay? Questions? No question. I'm going so fast, too fast? Or too fast? Well, I tell you, there is a lot of information to be given, and it's very important, I insist on it, that you should be prepared before coming here. Otherwise, instead of 14 weeks, that would take 30 weeks, which is not the point, okay? So I'm just trying to add something that you don't have in here, and by the way, we can retrieve that through the recordings of the movie, just in case you want to retrieve that. So please pay attention not to the details, but to the concept that I'm trying to transmit, okay? Okay, so we have reviewed the last lecture and today, we have reviewed a way to insert constitutive models, but in all cases, as you may remember, we have considered that the strain is the free variable so far, okay? We have considered the strain, then we have considered some internal variables. Sometimes the internal variable set was empty, and then we talk about, remember? When we have empty internal variable, no internal variables, we have the most general definition of a material that is called elastic. But in general, it's not. For instance, you just have seen a case in which the internal variables depend on the internal variables depend on the elastic strains, on some additional variables. Then the remaining are variables, the stresses and the free energy are dependent on that, and this. Okay? And then we just postulate a form of the free energy. We need as a third ingredient for derivation of the constitutive model the form of a free energy. For instance, in the last model, we have seen that this free energy depends in that way. Okay, and then we apply the Coleman's method, and we apply always that the stresses are derivative of the free energy with respect to the strains, and we obtain some expression of dissipation. But my point here is now, well, this provides a constitutive model in which the stresses depend on the strains, and maybe something else, internal variance and alpha. So we assume that the driving force of the constitutive equation is the strains. So if we know the strains, by replacing here and doing some operations, we obtain the stresses. What about the opposite, the other way around? So what about, is it possible to obtain the stresses, the strains in terms of the stresses? That is called the inverse constitutive equation. Okay, sometimes we need it. We may need it. Okay, we saw in elasticity that it's very easy to do that. But what about in general cases? What is the framework to derive a constitutive equation in which the stresses depend, or the strains depend on the stresses? So I assume that I know the stresses and I want to know the strains. Okay, so in that framework is trivial, almost trivial. Just start again taking in free variables the stresses. Just define the stresses as the free variables. Then, for instance, select some internal variables. For instance, let's consider just one internal variable, let's call it Q. And then, of course, provide the evolution equation that said that this internal variable has an evolution in terms of the free variables and the internal variables itself, so a function of sigma Q. Okay? And then the remaining variables are depending on these two. For instance, the strains are dependent variables. So the strain depends on sigma and Q in this setting. Okay? By the way, here appears a new letter that didn't appear before, that I have to introduce, which is called the Gibbs potential, which is useful in these stress-driven models. Why we use the name stress-driven? Because now is the stress who drives the model. Okay.
Does
Sorry, this is the stresses. Sorry, that's a mistake.
No, where is this?
The stress is the free variable.
The stress is the free variable and down the three.
And the strain. Okay. It's a mistake. So I will correct it. Okay. So this should be stresses, and that should be strains. Okay. Thanks. Okay. That's a mistake that still remains. So I will correct that after the class. You will find it corrected tomorrow or this afternoon, this evening. Okay. Anyway, forgetting that, we see that a new letter appears here, which is called the Gibbs potential, which is very common in theory of constitutive equation. What is the Gibbs potential? Well, if you were skilled mathematicians, I would tell you that this is just the Legendre transform of the free energy. Does any of you know what is a Legendre transform? No, it's not very difficult, but it's very used in constitutive equation. I will explain that in a few words again. That is a mathematical tool. Okay. Imagine that I have a function of one variable, x. Okay, phi of x. And then I define another function, which in principle is a function of x and y, which is defined in that way, the product of x of y minus phi of x. But what is y here? Y is precisely derivative of phi with respect to x. So whenever I have a function phi, I can construct this function, where this y is derivative of phi with respect to x, and that I can construct this function, okay? G is called the Legendre transform of this variable. And y is called the Legendre transform of this variable, okay? Well, we can say, well, yeah, and that, what is that? Why does it is used for? Well, the point is that this transformation has several interesting properties. For instance, in principle, G, as it is written here, depends on x and y. You agree? Well, it turns out that it doesn't depend on y. How is it proved? Look, let's do it. Let's consider the derivative of G with respect to x. Okay? That would be derivative of this with respect to x, which is y, minus derivative of that with respect to x, which by construction is y. So is y minus y equals 0. So the derivative of g with respect to x is 0. So the g doesn't depend on x. There's only a mistake here. G doesn't depend on x. Okay? That's first proof. And then we can see the following. Well, through that, implicitly, if y is defined in a way, x is a certain function of y. You can just invert the function and compute x as a certain function of y. Let's consider that in g, which I know that is just a function of y. Okay? G is a function of y, which is a function of y because x is a function of y, minus phi, that it's a function of x, which depends on y, function of y. So g, that is the way to construct g. Okay? But look, what happens if I differentiate g with respect to y? Let's do it. I differentiate g with respect to y is the derivative of x with respect to y times y. Okay? Plus x with respect derivative with respect to y, this is that. And then minus derivative of phi with respect to x plus derivative of x with respect to y. And I realized that this term are the same, so they cancel. So finally, the derivative of g with respect to y is x. So that assumption here is now reversed. If by definition I define y as differential, as the Legendre transform of x and defined as the derivative of phi with respect to x, then in the transform function g, which is the Legendre transform of phi, happens that by differentiation of j with respect to y, then I obtain x. So this is the summary. Okay? Given a function phi, I can obtain its Legendre transform just through that definition, which is this, fulfilling the following properties. That function depends only on y. In principle, should depend on x and y, but depends only on y. Second, the variables x and y are the transform of each other in the sense that y is the derivative of that with respect to x, and x is the derivative of that with respect to y. Okay, so set just a box, keep that into your drawer, and use that whenever you need it. That's what, this can be generalized to many components and blah, 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 blah. But the essence of the Legendre transform, again, French name here, that was the first one that used that for many purposes. That's very useful in mechanics. It's used in many aspects. So that's the Legendre transform. Now let's go back. Now that we know what is the Legendre transform, let's define the Gibbs potential as the Legendre transport, the Legendre transform of the free energy. Okay? So free energy, the free energy per unit of volume, rho 0 phi, is a function of epsilon. Okay? So let's consider epsilon and the function phi epsilon as the x and phi of x. Okay? That we had before. And, sorry, exactly. And next one, interesting material. Where am I? I'm lost now. Okay, here. So now we can transform that and transform this epsilon x into an y and this function into its Legendre transform. The Legendre transform of this function is called G, or G is the specific potential and rho 0 g is the density. You remember that this is per unit of mass, that's per unit of volume. Okay? So once I said that, now we know how do I construct G or rho 0 g as the product of sigma times epsilon minus that. That's the construction, that's the definition. That definition. We can say that, well, I mean, there are several physical explanations, but mathematically it's the same. And then it's fulfilled the following by construction, that the stresses, so that's the transform of that, is the derivative of that with respect to epsilon, and epsilon is the derivative of rho 0 g with respect to sigma. This that. Okay? That and that. Okay? By construction. It's just a mathematical argument. Okay? So that's why it's useful. So now I just, for instance, this is something that I can just consider, which is a function of the stresses, and which is the Gibbs potential. Okay, this potential is just a dependent variable that depends on the stresses. Look, that I'm not considering any internal variable, so the internal variables is considered an empty set. So conceptually, I'm defined, according to the definition I gave previously, an elastic material. Okay, so I should recover the properties of the elastic materials. Typically, a proportional dependence or linear dependence of the stresses versus the strains, in that case, the strain versus the stresses, and zero dissipation. Let's see. Okay, so now, what happened with that function here? Whenever I have, that is the construction, and can differentiate this equation, which is just the transform or the definition of G as the Legendre transform of phi, then I can differentiate that, and I obtain rho 0 g dot equal derivative of that, derivative of rho 0 g with respect to sigma times sigma dot, and that is, look, by definition, that the rho 0 g with respect to sigma is epsilon times sigma dot, sorry, exactly, epsilon times sigma dot. Okay, now about the dissipation. About the dissipation. This is the derivative. This is the function. We can take derivatives here. Then by derivation, differentiation with respect to time, rho 0 g dot equals sigma times epsilon dot plus sigma epsilon dot. That's the differentiation with respect to time of this product, minus rho 0 phi dot. Don't forget that rho 0 is constant because we are in the smallest range. In the smallest range, density is constant. And then we see from this equation that if I pass that term to the other side, I can obtain that sigma epsilon, this term, minus rho 0 phi dot is equal to that term minus this term here. So this comes out directly from this differentiation. And look, what is the expression of the dissipation? The expression of dissipation was precisely that. So that's the dissipation expressed in terms of the free energy. That is where we come from. But now, in virtue of this equality that comes directly from the definition of G, dissipation can be alternatively expressed in terms of G dot and in terms of sigma dot. And this is just a completely equivalent definition of dissipation, meaning the same, but now it's much more appropriated for models in which the driving variable is sigma. Because now, as you see here, it appears the variation of stresses, which is the free variable. Okay? But they are completely equivalent. So, now let's go to an elastic material. Before I came here, it was a mistake. An elastic material. An elastic material, define elastic material in terms of the stresses, so stress driven. We define a material in which the elastic material where the internal variables are an empty set. That's it. Okay? Then the free variables are the stresses, and the remaining variables, the stresses and the Gibbs potential, are dependent on the remaining, the free and internal, so only on the free variables in that case, which is that. Of course, if this is true, whenever I need to obtain the variations of epsilon and G dot, I have just to perform this derivative with respect to sigma. Okay? Okay, now let's consider the Gibbs potential. This potential, which is constructed that way. Then, according to what we have seen before, the stresses are derivative of the free energy with the strains, and the strains are derivative of the Gibbs potential with respect to stresses, due to the properties of the Legendre transform. Okay? Look, whenever I need in the dissipation what I see here, rho 0 G dot. Okay, rho 0 G dot, G depends on sigma, G dot would be the derivative of rho 0 with respect to sigma times sigma dot. But the derivative of rho 0 with respect to sigma is, we have H0, is equal to epsilon, rho 0 G with respect to sigma. So this is epsilon times sigma dot. Okay, so the expression of the dissipation is rho 0 G dot, which is epsilon times sigma dot, minus epsilon times sigma dot. What is this? If this is epsilon times sigma dot minus epsilon times sigma dot is 0. So dissipation is 0. I didn't postulate that. I have obtained that as a result. Okay? Again, for an elastic material, just reversing arguments using the Legendre transform, I've been able to find as a result that in an elastic material understood as that material in which the internal variables, there are no internal variables, so the internal variable set is an empty set, dissipation is 0. An elastic material, even if I define it as a stress-driven material, never dissipates. Okay? And what is the constitutive equation? Well, the constitutive equation is that the strains are the derivative of the free energy with respect to stresses. If I have the free energy, no, the Gibbs potential. If I postulate to define the Gibbs potential, I would have just to derivate, I had just to derivate, to differentiate that with respect to the stresses, and I would obtain the strains. And the dissipation is 0. Okay? So if we move back to the first slide defining the elastic material in the past lecture, I would find a relationship with that in which, in terms of the stresses, there were strains here, in which that was the stresses as derivative of free energy with respect to the strains, and dissipation is 0. Just one-to-one mapping from one problem to the other. Okay? Let's go ahead. And now, of course, the material will change depending on the Gibbs energy I define. I'm just trying to see that the same material model can be defined in an equivalent manner in terms of the stresses or in terms of the strains. That's what I'm trying to see. So imagine that I've just defined the elastic material model in terms of the strains. I've used the free energy. So now the Gibbs potential I have to use has to be the Legendre transform of the free energy I've defined. Okay? Because, of course, if I invent another material, another Gibbs energy, then, of course, we are not talking of the same material. So imagine that we had a material in which the free energy is, for an elastic material, a quadratic form of the strains. So that the stresses, that comes from the strain-driven model, the stresses as the derivative of the free energy with respect to strain are proportional to the strains through C being the elastic constitutive tensor, that in general depends on two parameters, as we saw. And of course, that equation, eventually, if I need it, could be inverted by multiplying times C minus 1 every of these sides, and I would attain the stresses equal to C minus 1 times sigma. So that is the inverse constitutive equation obtained for a strain-driven material. Okay? Let's see what happens if I am able now to derive the same equation, but starting from the other point of view, starting from a stress-driven material. Okay? And to do that, I just consider first the free energy, but now replacing, whenever I have the stress, the strain, I have C minus 1 sigma. I do that, I replace, and I obtain that the free energy in terms of the stresses can be written in that way. 1/2 of the stresses times the inverse of the elastic constitutive tensor times the stress. Okay? But I could also have found that, forgetting that, and defining the G as the, in addition, I now define G as the Legendre transform of phi. So, by definition is sigma times epsilon minus the free energy. But sigma times epsilon, which is C minus 1 sigma, in that way, that gives sigma C minus 1 sigma minus that, which is 1/2 of that. So 1 minus 1/2 is 1/2. So finally, the Gibbs potential, which is consistent with the free energy in the material, is that, a quadratic form of the stresses in terms of the inverse of the elastic constitutive model. Okay? So now that I have defined, now let's go back to the stress-driven materials. I need to define the stresses as the free variables. That doesn't exist. And then I need to define Gibbs potential. Gibbs potential is that. According to that, what is the constitutive equation? The strains are the derivative of this Gibbs potential with respect to the stresses. This is a quadratic form, so for derivation of that, it's like I have 1/2 of x times 1 over c times x. What is the derivative of this? The derivative of this, g, that is g. What is the derivative of g with respect to x? You know already, no? It's just twice, because this is x squared, 1/2 of x squared over c, is twice times 1/2 times x times c. Okay, so that is c times x. Okay, that's the same that happens here now in terms, 1 over c, 1 over c, 1 over c, that is 1/2, 1 over c times x, so that is 1 over c times x, so c minus 1 times x. This is what I have this here, right? Operating, following the same formula, but operating. You can do that by operating in terms of indices that you are supposed to be able to do.